All right, so hopefully you recall the central limit theorem and the stuff from the last couple of videos, essentially saying that as long as we know what the population standard deviation sigma is, the distribution of our sample mean is going to follow a normal distribution, right? So there's our standard normal distribution, and this thing here, that's our test statistic. That thing there is going to fall on this standard normal distribution. Okay. So far we've really only talked about statistics that follow this standard normal distribution. But realistically, right, there's not going to be many situations where we know what sigma is, where we know what the population standard deviation is. So in most real life applications, what we're going to do is we're going to use S to estimate. So we're going to use the sample standard deviation to estimate the population standard deviation sigma. Okay, and we can do that as long as the sample size is large enough. Now, by estimating, by going through that process, we've sort of replaced this sigma here in my test statistic with S, but it might change the distribution. So rather than following Z, the standard normal distribution, it's going to follow a new distribution that we haven't talked about yet, called the student's t-distribution. And this distribution kind of arises from the fact that there's uncertainty there in that S. Okay. It's related to the standard normal distribution. So the standard normal distribution, let's say it's something that looks like this. Oops, I got that wrong. So let's say that's the standard normal distribution. The student t-distribution is going to look something like this, right? So it's going to have slightly fatter tails. That's one way to sort of think of it. And the fatness of the tails is going to depend on a parameter called the degrees of freedom. So let's say that's the t-distribution with 30 degrees of freedom, okay? Having slightly less fat tails, go with that, right? So maybe that's the t-distribution with 100 degrees of freedom, okay? So as the degrees of freedom increases, as it gets bigger, the tails are going to get smaller and smaller, and the distribution gets closer and closer to the normal distribution. An alternative way of saying that is that, you know, as the degrees of freedoms get smaller and smaller and smaller, the tails are getting sort of fatter and fatter to sort of account for the fact that there's going to be a lot of uncertainty in our estimate, because our estimate of our sample size, or sorry, the estimate of our sample standard deviation S is not going to be as good when we have a small sample size. So in these particular examples, the degrees of freedom, it's sort of an extra parameter that's associated with the distribution. In this case, it's going to be given by n minus 1, the sample size minus 1. Okay. And we generally are going to denote the t-distribution as t and then a little degrees of freedom. In fact, I already kind of did that up here, right? This was the t-distribution with 100 degrees of freedom and the t-distribution with 30 degrees of freedom. So that sort of represents the entire distribution. If I want to talk about a specific value that falls on a t-distribution, so say this was the t-distribution with 30 degrees of freedom, if I want to talk about a specific value that falls on that distribution, I'm going to note it t and then the area to the right. So let's say this is the value here where this area is 0.05. So this is going to be t 0.05, comma, and then n minus 1, which in this case is 30. So whenever I add in that area in there, then I'm talking about this being a specific value, not just the whole distribution. So that's a little bit of notation for you.